We will discuss these questions from previous KTU examination on dynamics of machinery. The first question, derive the formula for natural frequency of free undamped longitudinal vibration using any two methods. So you can make use of Newton's equilibrium method, in which we establish a force balance, and the second method you can make use of energy method. Since it is a case of free undamped vibrations, which is basically a conservative system, you can make use of energy method, and these cases have already been discussed in our previous lectures. And there is also an additional part, also derive formula for natural frequency of free transverse vibration. In the case of longitudinal vibration, as in the case of a single spring mass system, in which you can get the natural frequency omega n is equal to root of k by m, where k is the stiffness of the spring in Newton per meter and m is the mass of the vibrating body attached to the spring. And in the case of free transverse vibrations, the natural frequency is given by omega n is equal to square root of g by delta, that is in radian per second. And if you want in hertz, f suffix n natural frequency is equal to omega n divided by 2 pi. So in the case of free undamped longitudinal vibrations, Fn is equal to omega n by 2 pi, that is 1 by 2 pi into square root of k by m. And in the case of the natural frequency of free undamped transverse vibrations, Fn is equal to 1 by 2 pi into square root of g by delta. Now we will solve a numerical problem from damped free vibrations. Remember, it is an underdamped system. A machine of mass 75 kg is mounted on springs and is fitted with a dashpot to damp out vibrations. It is a case of viscous damped system. There are 3 springs, each of stiffness 10 Newton per mm, and it is found that the amplitude of vibration diminishes from 38.4 mm to 6.4 mm in 2 complete oscillations. Assuming that the damping force varies as the velocity, determine the resistance of the dashpot at unit velocity, the ratio of the frequency of the damped vibration to the frequency of undamped vibration. Then the third part to be found out is the periodic time of the damped vibrations. Let's now discuss the numerical problem in detail. So here we have the given system, the machine mass 75 kg supported on 3 springs which are in parallel combination with a viscous damper. And here the stiffness is given as 10 Newton per mm, and in SI unit it will be 10,000 Newton per meter. So each spring stiffness, here it is represented by k by 3, because the total equivalent stiffness I want to represent by k, that's why it is represented as k by 3. Here the equivalent stiffness will be 3 times the stiffness of each spring. The total equivalent stiffness will be 10,000 plus 10,000 plus 10,000, since it is a parallel combination. So we have 30,000 Newton per meter, that is the equivalent stiffness here represented by k. And mass of the vibrating body is m, which is 75 kg in this case, and the damping coefficient is c. Here it is a viscous damped system. Initially you can find out the natural frequency of free undamped vibrations. So omega n is equal to square root of k by m, where k is the equivalent stiffness, that is 30,000 Newton per meter, divided by mass of the vibrating body, that is 75. See, whenever you use this relation, you please make sure that the spring stiffness is in Newton per meter. So 30,000 divided by 75 and under root of that, so you will get 20 radian per second. That is the natural frequency of free undamped vibrations. Now in viscous damping, you know that the amplitude of vibrations diminishes exponentially. that is exponential decay. So in order to represent the exponential reduction of amplitude in a viscous damped system, we have a term called logarithmic decrement delta. Logarithmic decrement actually is the natural logarithm of the ratio of successive amplitudes of vibrations. So if you take natural log of x0 by x1 or natural log of x1 by x2 or natural log of x2 by x3, you will get logarithmic decrement delta. After n oscillations, if you write x0 by xn, then that will be e raised to delta whole raised to n. See, logarithmic decrement, if you take the antilog of this relation, that is x0 by x1 is equal to e raised to delta. Similarly, this is same as the case of x1 by x2, x2 by x3, x4 by x5 and so on. So x0 by xn, the product of all such ratios together will be e raised to delta whole raised to n. So that is e raised to n delta. And if you take the natural log of this, so you will get ln x0 by xn is equal to n into delta. So you have an important relation like this representing the connection between the amplitude initial one x0 and after n oscillations xn. So the ratio is x0 by xn and its connection with the logarithmic decrement. So the logarithmic decrement delta is equal to 1 by n into ln x0 by xn, natural log of x0 by xn, where x0 is the initial amplitude and the amplitude reduces to xn after n oscillations. So here it is given that the amplitude diminishes from 38.4 mm to 6.4 mm in 2 complete oscillations. So here n is equal to 2 and x0 is, you can take 38.4 and xn, that is x2, so that is 6.4. So the relation delta is equal to 1 by n into ln x0 by xn, that becomes 1 by 2 into natural log of 38.4 divided by 6.4. So you will get logarithmic decrement delta as 0.8959. We know that in a viscous damped system, the damping force F suffix d is proportional to the velocity of the vibrating body. Even that statement is given in the question. Fd is proportional to x dot. So Fd is equal to a constant c into x dot, where this constant is known as damping coefficient. So damping coefficient actually is the ratio of the damping force to the velocity. So here in this question you are asked to find out the resistance of the dashpot at unit velocity. What does it represent? It is nothing but Fd divided by x dot. So if you take Fd, damping force or viscous resistance, divided by x dot, that is the velocity, you will get c. So indirectly this is a way of finding, or you are asked to find out the damping coefficient c, which is equal to Fd by x dot. And what is the unit of damping coefficient? Damping force Fd has the unit Newton divided by velocity meter per second. So therefore Newton by meter per second. So the unit is Newton second per meter. You have a relation connecting the logarithmic decrement and the damping factor or damping ratio. So damping ratio, here it is represented by epsilon. So it is also denoted by theta. So epsilon here, that is damping factor or damping ratio. That damping factor or damping ratio is actually C divided by Cc. That is damping coefficient in the vibrating system divided by its critical value Cc. So C by Cc is equal to epsilon. So here delta is available and you have a relation delta is equal to 2 pi epsilon divided by square root of 1 minus epsilon square. And if you make some algebraic manipulation, you can write epsilon in terms of delta. So you square this relation, you will get delta square is equal to 4 pi square epsilon square divided by 1 minus epsilon square, and then cross multiply that. So you will get 4 pi square epsilon square plus delta square epsilon square is equal to delta square. And if you group it, that is taking epsilon square common, you will get 4 pi square plus delta square within bracket, that is equal to delta square. And you have to find out epsilon. So epsilon square is delta square divided by 4 pi square plus delta square. So if you take the square root of the expression on the right hand side, you will get the epsilon, that is damping factor or damping ratio. So damping factor epsilon in terms of logarithmic decrement is given by epsilon is equal to delta divided by square root of 4 pi square plus delta square. So here we have already found out delta, the logarithmic decrement is 0.8959. And if you substitute in this relation, you will get epsilon. So epsilon is equal to 0.8959 divided by square root of 4 pi square plus 0.8959 square. And if you simplify, you will get epsilon is equal to 0.14116. So the value is less than 1. Obviously, it is an underdamped system. Only the underdamped systems only will vibrate. So epsilon is less than 1, that is underdamped vibrating system, and damping factor or damping ratio represented by epsilon is equal to 0.14116. Now epsilon is equal to C by Cc. C is the damping coefficient which we have to find out, and Cc is the critical value of the damping coefficient. How do you find it out? We have a relation, critical damping coefficient Cc is equal to 2m omega n. So here mass of the vibrating body is 75 kg, omega n natural frequency of undamped vibrations we found out initially, that is 20 radian per second. So if you substitute over here, you will get Cc is equal to 2 into 75 into 20, which is 3000 Newton second per meter. So that is the critical value of the damping coefficient. So that is 3000 Newton second per meter, and epsilon, that is the damping factor or damping ratio, is 0.14116. So if you make use of these two, what you can get is the damping coefficient C. So damping coefficient C is equal to epsilon into Cc. Epsilon is 0.14116 and critical value Cc is 3000. So epsilon into Cc, if you take the product, you will get 423.48 Newton second per meter. So that is the value of the damping coefficient. Remember, here in the question, it is you are asked to find out the damping force at unit velocity. That is nothing but the damping coefficient value itself. And now further, the ratio of the frequency of damped vibrations to the frequency of undamped vibrations. So frequency of damped vibrations, the natural frequency of damped vibrations, that is omega d, and the natural frequency of undamped vibrations, that is omega n. So omega d divided by omega n, you have to find out that ratio, or you can say fd by fn. And we know that omega d, that is the natural frequency of damped vibrations, see, that is related to the natural frequency of undamped vibrations by the relation omega n into square root of 1 minus epsilon square is equal to omega d, where epsilon is damping factor. So we know the value already, 0.14116. So omega d by omega n is equal to square root of 1 minus epsilon square. So what you can get is, if you substitute the value of epsilon here, that ratio comes out to be 0.9899. So it's very close to 1. Since the damping ratio is very less, omega d and omega n are more or less the same. So omega d in this case will be 0.99 times omega n. So omega n here is 20. And what is the value of omega d? Omega d will be 20 into 0.99, that is 19.8 radian per second. Therefore, the natural frequency of damped vibrations in radian per second, omega suffix d, is equal to 19.8 radian per second. The third item to be found out is the periodic time of damped vibrations, that is t suffix d. You know that t, the periodic time, t suffix d, here D stands for the damped vibrations. So time period of the damped vibrations, or you can say the time required for one such damped oscillation, is represented by Td. So Td is equal to 1 by Fd. And what is Fd? Fd is omega d by 2 pi, and Fd is in hertz. So 2 pi by omega d if you take, so you will get the time period. So what is this Td? Td is equal to 2 pi by omega d is 19.8 radian per second. So if you substitute over here, you will get the time period of this damped vibrations is equal to 0.317 seconds. That is the time taken for one such damped vibration is 0.317 seconds.